Brown dwarf. This is a star that almost existed. It forms the same way as every other star, but stops just before the ignition. It doesn't have a steady fusion or real light, just a warm, fading object drifting through space. It's the universe showing that even something as powerful as a star can fail before it truly begins. Red Dwarf. This is the slowest burning star in existence. It uses its fuel so carefully that it can live for trillions of years. While bigger stars explode, collapse, and disappear, red dwarfs barely change at all. Most stars in the universe are like this: small, quiet, and almost impossible to outlive. Orange dwarf. This is where things start to feel stable. Bigger and brighter than red dwarfs, but still long lasting. These stars can shine for tens of billions of years. They don't rush, they don't collapse early, they just exist in a steady balance, making them some of the most reliable stars in the universe. Yellow dwarf. This is the kind of star we orbit. It looks calm, constant, almost permanent, but inside it's slowly changing. Every second, it's converting hydrogen into helium, building pressure for what comes next. It may last billions of years, but it is already moving towards its end. Blue main sequence star. This is what happens when a star is too massive to stay stable. It burns hotter, brighter, and faster than almost anything else. But that speed is a problem. These stars live fast and die young, sometimes lasting only a few million years. The brighter they shine, the closer they are to collapse. Red giant. This is what a star becomes when it starts running out of fuel. The core shrinks, but the outer layers expand massively. It grows so large that entire planets could be swallowed inside it. What once was stable now stretches outward, becoming something unstable and temporary. Blue giant. This is a star pushing itself too hard. It shines intensely, radiating huge amounts of energy while losing material at the same time. It's powerful, but it cannot hold that power for long. Every moment, it's burning through its future. Red supergiant. This is where size stops making sense. These stars expand to enormous scales, large enough to engulf entire planetary systems. But inside, something more important is happening. Heavier elements are forming, layer by layer, pushing the star closer to a sudden collapse. Blue supergiant. This is one of the most extreme stars that can still hold itself together. It burns at incredible temperatures, shines with overwhelming brightness, but everything about it is unstable. It's not just shining, it's struggling to survive its own energy. Hypergiant. Everything here is breaking apart in real time. Hypergiants are so massive and unstable that they can't even hold themselves together. They constantly shed enormous layers into space, like a star tearing itself apart before the death arrives. Rare, chaotic, and short lived, this level of brightness is not power, it's collapse already in progress. White dwarf. What remains is small but brutally dense. After a star sheds everything it had, the core is left behind. Hot, compact, and slowly fading. No more fusion or more energy is being created. Neutron star. Now, matter itself starts to break the rules. After a violent collapse, the core is crushed so hard that atoms can't exist anymore. Everything is packed into something insanely dense, spinning at extreme speeds, sometimes blasting beams across space. This isn't just a star anymore. It's a matter pushed beyond what should be possible. And the final boss, black holes. When a star collapses into itself, it forms a black hole. Gravity in the black hole is so strong that not even light can escape it. There is no surface, just the event horizon. Matter around it gets ripped apart and heated, shining brightly before falling in. Anything crossing the horizon is crushed to a point of infinite density. If you like interesting science, subscribe.